this is our class on trying to use all our pieces, the various pieces that you have learned, into doing a full structural evaluation. Okay, even though the title says calculating reaction forces in a truss, actually we are going to look at the general method for calculating reaction forces. All of them are in 2D, and you will see that the calculations are pretty simple. Okay, so let's start. So, a couple of things so that we make sure, in order for a body to be in equilibrium, which means either it's stationary or moving at constant velocity, which means magnitude of the velocity, that's the speed, has to be constant, direction of motion has to be constant. If those two conditions are met, the net force acting on the body and the net moment acting on the body should be zero. So what happens if the net force is not zero but the moment is zero? Sorry, if the net force is zero, and what if the net moment is not zero? The body will spin. Conversely, if the net force is not zero but the net moment is zero, then the body will translate. If both of them are zero, if both of them are not zero, the body will translate and rotate. Okay, we saw that, we know how to do that. So we will do some examples to show how to use this to determine unknown external forces, provided you know that the body is in equilibrium. Okay, so this is our structural evaluation process. Remember, for this you have to be able to find out force vectors, you have to be able to find out moment vectors. That's why we did those things in the beginning. So let's look at an example problem, and you will see our process is pretty straightforward. So I have an object that looks like this. So there's a joint here and it's touching the ground here, and this angle is 60 degrees and all that. The dimensions are given, and we have to determine, when they say reactions, that means what are the constraint forces at A and B. So we are going to do this problem and we will try to figure out. The steps are very simple. First, I have to figure out what is my system, isolate the body. Second, I want to identify and mark the external forces on the free body diagram. You know, you draw these free body diagrams, that means you should know what kind of joint is this and what kind of joint is that and all that we did in the first week of class. We are looking at that again. Then we are going to create a force table which will list the forces and the points at which they act. Then we are going to apply the equations of equilibrium. So this step, going from here to step 2 to step 3, is the start of our process of converting pictorial to vectorial. So this is all pictures, step 1 and step 2. Step 3 is mostly our vectorial calculations and things like that. Step 4 is the new stuff, which is, we are now going to say that the sum of all the forces, sum of all the moments are zero. You will get equations. Then you have to see if you have enough equations. If you don't have enough equations, you have to go back and see what else you could do. And then if you're able to solve the equations, you can go and complete. So let's take a look. Okay. First thing to do is isolate the body. Watch, and there you go. Can you see the body has been isolated? Notice I drew only the outline. I don't care about anything that's inside, and I marked points A, B and G. Point A is where there was a hinge, point B is where there is a roller, and point G is where there is gravity. Okay. Now next, what are we going to do? We are going to write down all the forces on that. But before you do that, you should always put the axis, because this is what will help you decide. And the typical trick here is to try and put the axis at a point which is a pivot. In this particular case, the hinge or pivot is at A, and it's better to put the axis like this. You have choice. You can put the axis in any direction you want, but you have to decide which way to put. Then we are now going to identify and mark the external forces on the free body diagram. Draw all the forces on the free body diagram. So let's start at the pin A. Is it obvious to you at pin? It's a pin joint, so there are two forces. You remember this thing, AX and AY, because it allows free rotation, does not allow translation in the X direction, does not allow translation in the Y direction. They are drawn in blue because they are unknown. Okay. Now this is actually a roller joint, even though this is a typo. It should not say pin joint at roller, it should just say roller joint. And for a roller joint, the force is actually, because it's an undriven roller, there is no driving on this, So it's just a free roller. So the force will be perpendicular to the roller. There you go, like that. Okay. Then gravity at point, and we know that the weight is 40 pounds. That's given to us. So I've drawn that. So that's drawn in green because that's known. So these two forces are unknown. The red arrows tell us what are the coordinate axes, and the blue arrows tell us what are the unknown forces. Anything else? We are done. Excuse me. Okay. Now next, what do we do? Just remember, always put the axis at the pivot. It will save you a lot of pain. And blue arrows are unknown, green are known. So now we are going to list force points of action and moments. Okay. So the way we do that is we create a table. So this is the interesting thing. So we're going to look through each point, write the force at that point, Fx and Fy, and the location. Let's see. Point A. Can you see that point? There are two forces, one in the x direction, one in the y direction. They are both unknown. The location we know, they are both at 0, 0. Okay. Point B. Now you have to be careful at point B. I don't know whether you can see that the angle is 150 degrees. So remember, I have to put an axis at the base of this vector and compute the counterclockwise direction of this vector. Don't put an axis here and say it's 60 degrees or 30 degrees or something. Please be careful about this angle. Again, it's trig. If you put that angle, then I have B cos 150 in the x direction, B sin 150 in the y direction. You don't have to worry about the sign if you measure the angle counterclockwise from the positive x direction. Where is it? From here to here, XA is 20, YA is minus h. You can see that. That's 10 plus 10, 20 inches minus h. So 20 minus h. Okay. And then the last point is G. Where is G? It has to be in the center of this, no? So there is no x component at G. The y component at G is 40. And then let's say minus 40 because it's the negative y direction. The x location is 10, y location is 6 minus h. Well, what's 6? That's the center of this thing, and h is that, so that distance is 6 minus h. So writing these numbers and getting these things requires a little bit of trig, and that's where you have to be good at it. Okay, so this is all the forces and where they act. Now we can compute the moments, and we know how to do that now. xfy minus yfx. So I'm going to show you. There. Moment equals xfy minus yfx. So let's fill out for each of them. There. X and y are both 0, so that's 0. Now that one is 20 times b sin 150, which is 10b, and minus h times b cos 150, which is minus 0.66 hb. And then this one is 10 times minus 40, minus 6 times 0, so that's minus 400. Okay. So we return all the forces and the corresponding moments. Then what do you do? It's pretty easy. What we do is we sum all the columns. I'm going to sum these three, set it equal to 0 because that's the net force in the x direction, net force in the y direction, net moment on the body. So sum this, set it equal to 0, sum this, set it equal to 0, sum this, set it equal to 0. So let's see what we get. If I sum this, I'll get ax plus b cos 150 plus 0 equal to 0. So this ax minus 0.866b equal to 0. Okay. Next, ay plus b sin 150 minus 40 is the same as ay minus 0.5b minus 40 equal to 0. That's the second equation. And the last one is this 0, 10b minus 0.866 hb minus 400 equal to 0. And this is counterclockwise moment. This tells me which way is positive. Okay. After a while, you don't necessarily have to do this table. You can directly write out these equations. There's nothing that says you have to do this table. You know what I mean? But diagnostics wise, it's very nice. I will do it because I just want you to get into the habit of doing it in a clean way. And then notice all the units are here. Can you see that? Inch, pound, inch, so on. Now, let's see if we have enough equations for unknowns. Let's see how many equations do we have. We have 3 equations. How many unknowns are there? Ax is one unknown, Ay is the other unknown, and B is the other unknown. So I got 3 equations, 3 unknowns. Hey, I'm home free. I don't have to add anything or subtract anything or anything. So I've done my count. I know that there are enough equations for unknowns. So let's start solving. So first thing to do, solve for B from here, and it will turn out B is 400 over 10 minus 866H. So B is 400 over 10 minus 8.866H. For H equal to 0, B is 40 pounds. For H equal to 8, B is 130 pounds. Excellent. Once you get that, you can substitute and you can find Ax and Ay. There you go. And we are done. Okay. The whole idea is that if you write the force components in tabular form and if you use mx equal to xfy minus yfx, you will get an idiot proof way of doing the equations. It is very difficult for you to go wrong in this method. Okay. So please remember the critical point here is getting this force table. Once you get this thing, writing out the equation, no big deal, we are done. So converting this picture into this force table is where really your talent lies. Okay, so please learn how to do that. Before we go, I want to make one more point, which is that some of you have this idea about that you can also do it by doing leverage. You know what I mean? Drawing a parallel line and so on. I want to show you with an example that doing this or xfy minus yfx will give you the same answer. So suppose I have force shown here, 20 pounds, 45 degrees and acting at the point 3, 2. Can you see that? X is 3, y is 2. So there are 2 different ways of doing it. One way to do that is by drawing these parallel lines. Can you see that? And measuring that gap distance. It will turn out to be 0.707. So you can compute force times the gap distance. If I want to find the momentum at this point, force times the gap distance will give you 14.14. And if I look at this point O, it's getting turned counterclockwise by the force F, and so it is CCW. Okay. Now let's do it by using our Cartesian notation. There. First I take force and I write it as Fx is F cos 45, Fy is F sin 45, X is 3, Y is 2. So let's do that. Xfy minus Yfx, you will get exactly the same answer. You see that? Exactly the same. Please stare at these 2 things. Make sure you convince yourself that doing either of them is identical. Thank you very much.